So today's lecture is going to be on gases. We're starting chapter 5. We completed chapter 4 in our last set of lectures. So the date of this taping is 9/10/2020, September 10th, 2020. So I know some of you are on chapter 4. Some of you are at different places or parts in the course. So just to try to get us all on one wavelength, things that you guys should be working on for both sections, Monday, Wednesday, Friday, and Tuesday, Thursday, is you should really be finishing up chapter 3 homework, and we really should start working on and wrapping up chapter 4. Okay, so whatever is important on the test is on the study guide, and also as well as your homeworks. And also we should begin looking at chapter 5. This is towards the lecture part of the course. And also a couple of things to try to help you are those clutch prep drills. Okay, so chapters 3 through 5 is something that you guys should be working on at your own pace, but do not fall or lag behind. And also work on quiz 2. The exam is the last day of September, and I believe that is the 30th or the 31st. Again, it depends if you're Monday, Wednesday, Friday, or Tuesday, Thursday. I believe it's 30th and October 1st, dependent on your section. Okay, Tuesday, Thursday versus Monday, Wednesday, Friday. As far as labs are concerned, we really should start turning in our 2 lab reports. The labs that we should be have already turned in should be the very first lab on density of water, and then the nomenclature lab. What's in our rotation now for you guys to do is aqueous reactions. So I'm going to say now that's in our rotation is aqueous reactions and limiting reagent, which is sort of a computer-based lab. Gets you an idea about limiting reagent. There will be a limiting reagent problem on your second test, which is, the same date as when your quiz 2 is due. So this is sort of a snapshot of where we should be at, and so make sure you're keeping pace and always try to get ahead as best as you possibly can, given all that's going on. So let me talk in this lecture, this tape lecture, on gases. So we're not talking about solids, we're not talking about liquids, we're talking about sort of what is called the third state of matter, which is gases. And gases have corresponding gas laws. So here is what we're going to be talking about now. Okay, exclusively gases. Okay, what they do, some of their properties, some of their behaviors. One thing about gases, they're not really tangible to our physical senses. Unlike a solid, which we could bang upon, hit, describe in terms of whether it's rough or smooth, or if it's scaly, something tangible. Liquids are also tangible to our physical senses. We can measure a volume, we can describe its color, we can describe how thick it is versus how non-thick it is, viscosity. Gases cannot be really measured by any of those descriptors, both physical descriptors, in terms of tangibility. So gases are very much invisible. There's one property of gases that some can recognize, and that is smell. But for the most part, gases are something that we just detect. They are a state of matter that we really cannot, quote unquote, putting it in quotation marks, see. So it's a detection. And also notice the molecular arrangement of gases. So the atoms or the molecules of a solid tend to be organized in some sort of lattice structure. And the atoms or the molecules of a liquid, they tend to be a little bit apart. There's some distance between individual liquid molecules, say for example water, and gases are the one extreme. Well, they're not so clumped together like solids, but they are really separate. And in fact, they slosh around and move around more so than liquids, such that if you open up a container of gas, it will permeate a room, whether the room is a closet or whether the room is a classroom. So a couple of behaviors of gases that I'd like to talk about here. Gases diffuse, and by diffuse they mean what I mean is they kind of spread out. They sort of permeate. So they can go all the way to the corner of a room, or they can just, they just occupy the space that's around it. So that's a diffusion. So the behavior of a diffusion is they kind of, just move around. And then also as they move around, or diffuse would be the better term, as they diffuse around, what they do is they collide. And the collisions can be with another gas molecule. It could be with its own partner. It could be, like I said before, let's call it a yellow one, another gas molecule. Or what is also common is that it could collide with the container. Okay, so if we enclose the gas, this gas molecule can hit the container, it can hit the yellow gas molecule. So that's how we describe one aspect of gases in terms of their motion. Their motion is not a single number. It's sort of like an average. It is an amalgam. It is an amalgam of all these different diffusionary speeds, and we call that a root mean square speed. So it's not just one speed, but sort of a collection of all the gases and their diffusionary speeds, and we call that collectively one number the root mean square speed, which has its own equation, which we'll talk about in the next, towards the end of the chapter. There's no real physical tangibility to this. We cannot touch a gas. We certainly can smell a gas. Some gases we cannot smell, such as carbon monoxide. As an example, let me give you two gases. One is something that smells really bad. That's hydrogen sulfide as a gas. It has the smell of a rotten egg. Okay, versus something that's invisible and very toxic. That is the odorless, colorless carbon monoxide gas, which can be very dangerous because it displaces oxygen. Both of these are gases. Both of these diffuse. You wouldn't know them, but one of them you can smell, the other one is just innocuous. It takes the shape of whatever container you put it in. So they take the shape of the container. Or even the room, right? You can take the shape of the room, the closet, the closed container, or a container of 4 different gases. So here's my container. I'm going to have an orange gas that I'm going to call a triangle. So we have the triangle gas that is symbolized by an orange triangle. Okay, we have a yellow circle gas. Okay, I'm going to put 5 of them here. We'll have one of the one gas that's square. Okay, so we got 2 of the orange triangle gases. We got 5 of the yellow circle gases. We got 1 square gas, and let's just do one more. I have 8 of the purple gases. Okay. So I have 4 gases: purple, orange, yellow circle, and then blue square. So in this container, totally enclosed, I have 4 gases. Remember, we stated before that gases diffuse. Okay, so they're going to just move around, sort of random, willy-nilly, and the only thing that prevents them from going straight and moving on in their path is the container. Right, the container, so they'll bounce off or sort of ricochet off the container. It's like this orange gas will bounce off this. So they're going to just sort of diffuse along their merry little way. The question now is, which gas has the more number of moles? All right, moles. Which gas, orange, purple, yellow, the square, which of these 4 gases has the more number of moles? We're going to call that moles N. Okay, that's our first sort of variable that describes a gas's number of moles. And we're going to label that N for number of moles. And so the question I have to ask you is, which one has the most number of moles? And you'd be correct if you said it was the purple one. Okay, this purple square has the most moles. Remember, this has 1, 2, 3, 4, 5, 6, 7, 8 molecules of gas, so more number of moles. The second most would be the yellow circle at 1, 2, 3, 4, 5. So the number of moles will be, for the purple gas, the most number of moles. So moles is one behavior of gas we can describe, or one variable that describes the behavior of gases. Another variable that we can describe gases is volume, because you see, if I have a container of all these four gases here, what I can do in the bottom is sort of squeeze this or compress this. So I'm going to draw this exact same thing, but I'm going to draw it in a volume that's much, much lower. Right, so now I've shrunken my volume, sort of this boxed container. It has moved from this dimension to this much smaller dimension. So remember what we stated before is these gases diffuse, so they're going to diffuse, but we sort of shrunken the box, haven't we? We moved the box, and now there's less space for these gases to diffuse, which also implies pressure. Okay, so this is another variable that we can use to describe the behavior of gases, pressure. So the question is, which gas contains the most pressure, or exerts the most pressure is how we really say it. So two things I want to mention here. The gas that exerts the most pressure is the purple gas. It's the one that has the most number of moles. So there's just more of it around. So there's more propensity to collide. So that exerts the most pressure. But notice the relationship with volume and pressure. What do you think the pressure of the whole container would be as we reduce the volume? So another way of asking you the question is, which would have more collisions, which would have more pressure? The volume that's this big or the volume that's this big? Okay, which would have more pressure within it? So what I'd like to convince you is that the gases in the much larger container exert less pressure, less collisions, than the gases in the smaller container. More collisions, more pressure. So we already have a relationship between between some of the variables that describe a gas, and that is the pressure-volume relationship. So again, a big container, less collisions, less pressure, because the gases are diffusing and they're in a very, very large space, occupied space. Okay, if we squeeze it, or compress it down to the size of a box or a closet, the gases are still diffusing, but they're hitting each other more, they're colliding with one another more, they're hitting the container at a faster rate than at the larger volume. So this brings us to a relationship between the pressure of a gas that it exerts and the volume of the gas, and that is an indirect proportion. So as we can state here, that if you increase the volume of a gas, you're actually increasing the volume, you're decreasing the pressure. If you decrease the volume of a gas, you are increasing the pressure. Okay, so this is what's called an indirect relationship. One goes up, the other goes down. So as your volume goes up, actually let's just say as the volume goes down, tighter space, more collisions, more hitting upon each other. As the volume goes down, the pressure goes up. And then, we can say the same thing. As your volume goes up, there's less chances of collision, less force per unit area, and the pressure is going to go down. The pressure exerted goes down. And the fourth and final component that influences the behavior of a gas is temperature. And for here, the very important point is that temperature must be expressed in kelvins. So kelvins for the temperature of a gas. Temperature is going to be 273.15. A lot of people just go with 273, which is fine. 273.15 plus degrees C. Okay, so that's how you go from degree C to Kelvin. You add 273 to it. So if your temperature is in degree C, add 273, you'll get it in Kelvin. So that's the temperature in Kelvin. Let me put it here in Kelvin K. Now, temperature and pressure, that is a legitimate relationship. If you increase the temperature, you're increasing the speed of the gas. What else will you increase? You'll increase the pressure because you have more collisions. Okay, more speed, more collision frequency, more pressure. So here is another relationship here. What we were saying is that as you increase the temperature, the pressure actually goes up. Okay, more collision frequency. And that is called a direct relationship. Okay, on the flip side, if you lower the pressure, the molecules of the gas do not do not hit each other. The collision frequency is less, so the pressure goes down. So as one goes up, temperature, the pressure goes up. As the temperature goes down, the pressure goes down. That is called a direct relationship. If you increase the number of moles of a gas, think you're inflating a tire. If you're increasing the number of moles of a gas, you're increasing the volume. So this is another direct relationship. Okay, so one goes up, the other also goes up. Right, so moles of a gas describe its behavior. Volume of the gas is one way we can describe the behavior. Pressure of the gas is one way we can describe the behavior. And then temperature of the gas is one way we can describe the behavior. Some relationships between two of the four. As your number of moles goes up, okay, the volume goes up. Okay, an indirect relationship, this is called Boyle's law. As the volume goes down, the pressure goes up. And then another relationship here is that as your temperature goes up, the pressure goes up. That's a direct relationship. By the way, this is called Charles' law. This is called Boyle's law. And then way up here, sort of the inflation of the tire type of deal, inflating a tire or inflating a basketball. This is called Avogadro's law. V, number of moles, and temperature T, that has to be in Kelvin, remember that. Okay, this is where a lot of mistakes happen. Okay, must be in Kelvin. We can unify all of these together with one relationship, and that one relationship is called the ideal gas law. And here's the ideal gas law, PV equals nRT. So these four behaviors or properties of the gas, of an ideal gas, this is called the ideal gas law, sort of unified by this gas constant R. So let's just reiterate, P is in pressure, and the pressure is going to be in units of atmospheres. All right. Remember, more collisions, more pressure. V is volume that the gas occupies. This is the pressure that the gas exerts. V is the volume it occupies. So pressure gets exerted. Okay, the units here are going to be liter. Okay, a volume is something that a gas occupies. T is temperature, and that has always going to be in units of Kelvin. Kelvin K. And again, Kelvin K is degree C plus 273, or 273.115 if you want to be technical. N is the number of moles. Okay, so you can have grams of a gas and we can convert it to moles of the gas, and that's N. All of these are unified by R. And R is what's called a universal gas constant. That is something I'll give you on the exam, so do not memorize this. And R is going to be, if you look this up on the internet, there's actually, it's very interesting, there's 12 different versions of R. Okay, but the one, we're going to use two versions out of those 10 or 12. And this version for the ideal gas law is 0.0821 liters atmosphere divided by mole Kelvin. Okay, so that is going to be R here. Okay, the universal gas constant is what it's called, and it's something you do not memorize, and I'll give that to you on any exam. Okay, so looking here, a lot of the gases are in the non-metal window of the periodic table, and a lot of them are diatomic. Okay, classic example is O2. Okay, another one in our atmosphere is H2. Okay, we also have N2 here. So a lot of them are diatomic, and a lot of them are non-metals on the right-hand side of the periodic table. So this table shows some naturally abundant gases. The key word here is naturally abundant. So basically at normal temperature and normal pressure, these exist as gases. This is how you'll naturally find these on Earth, right? You'll naturally find oxygen as O2. Okay, there is a higher levels of the atmosphere, you'll have O3. Some compounds, probably you're all familiar with the gas carbon dioxide. This is the nasty carbon monoxide. I think that's somewhere here. Yeah, the enemy, because it's so bad for our lungs. So a lot of compounds exist naturally as elements, natural abundance, room temperature, and ambient pressure. And a lot of standalone elements at room temperature, at normal pressure, exist as a gas. All right, brief discussion on units of pressure. So Pascal is 1 unit of pressure. Remember, it's a force. It's a force per unit area. And that's something you'll see. We're going to use atmospheres and millimeters of mercury. Okay, and that's the conversion between the two. So this is the one that gets the most, at least in this class, this is the one that gets the most bang for your buck. Okay, so yeah. 1 atmosphere is that many millimeters of mercury. Some properties of gases. A lot of these are, I believe, a little self-explanatory, so let me quickly go over them. Like a liquid, they will just take the shape of the container. They can occupy the whole room. They can occupy the closet. They can occupy Earth. Okay, so they spread. You can compress a gas. So think of inflating a tire and deflating a tire or a basketball. Gases really do not partition. Okay, it's not like oxygen gas will stand by itself and carbon dioxide gas will stand by itself. If you inject oxygen and if you inject carbon dioxide, they'll mix. It's not like they'll want to get away from one another. It's not like oil and water. Okay, some liquids really hate each other and they'll separate or partition. Gases, you don't see that. So you can mix in 3 gases, 10 gases, 100 gases. They'll all mix together in the environment. Gases have generally a lower density. Heavier gases will rise to the atmosphere. Also, heavier gases will diffuse slower. And it makes sense. If you have a big, fat, bulky gas, it's not going to move as fast. So diffusion, this root mean square speed, which is a measure of how fast a gas diffuses, our term for how fast a gas moves. The diffusionary rate is slower if the gas is heavier. So, say before gases diffuse and spread out, we have an equation to describe gas diffusion. And the higher the pressure of the gas, the more collisions occurs. Pressure, when you're thinking of pressure, think of collisions, whether with another gas molecule, whether it's with the container. The more probability of it colliding with something else, the more pressure that specific gas exerts. Talked a little bit about the gas laws here, PV equals nRT. There's a mistake here in your notes. You will have the proper value of R, but this is the correct version of R. So that's R, and PV equals nRT. This is called the ideal gas law. A lot of gases do not behave ideally. Ideal gas law means they follow these 6 or so behaviors. Now comes an important part of the course, and that is STP. STP is a specific temperature, and it's a specific pressure. Okay, the specific temperature is 273 Kelvin, which you should now know all gases, you need to convert it to Kelvin. And it's a specific pressure, and that's 1 atmosphere. Okay, that's it, and that's all. That's what standard STP signifies. And if we have 1 mole of that gas at STP, okay, so if we have 1 mole of an ideal gas at STP, the volume will be 22.4 liters. Okay. Have 1 mole of an ideal gas at STP. Okay. It's important that we are at STP. 1 mole of an ideal gas at STP have established are these 2 conditions, nothing more, nothing else. Then we have 22.4 liters of volume. 1 mole is not STP. Okay, it is not STP. Okay, STP is just 2 conditions: a pressure, that's 1 atmosphere, and a temperature, that's 273 Kelvin. Right? It just so happens if you have 1 mole of that ideal gas, then you're occupying 22.4 liters. Right? So 1 mole at STP will have 22.4 liters of volume. Assume we have a gas at STP. Some of these gases are very heavy. Some of these gases are very light. Some of these gases are required for us to breathe. Some of these gases are toxic. But the key note I want to tell you guys is that if you're at STP, which remember is 1 atmosphere and 273 Kelvin, if you're at STP, okay, and if you have 1 mole of all of these guys, they will all occupy 22.4 liters. Okay, so that's the amazing thing. Okay, no matter the size, shape, weight, how fast do they diffuse, how slow they diffuse, if you're at STP and you have 1 mole of any of these gases, they will occupy 22.4 liters, regardless of the type of gas. But it's PV equals nRT, and if you solve for V, isolate V. Okay, N is 1 mole, because remember you have 1 mole. R is the gas constant. Temperature is STP, temperature. P is STP, pressure, and if you put all those in and solve for V, you'll get 22.4 liters. All right, a little bit about when gases collide with one another. So when gases collide with one another, we tend to say that their interactions are inelastic. Excuse me, their collisions are sort of elastic. Okay, so there's really no energy exchange. I'm not going to really test you on this, but this is part of the kinetic molecular theory. But the idea is that there is no energy exchange that's occurring when 2 gas molecules combine with one another. Okay, again, not an important point that I'm going to emphasize on in terms of the test. And gases are generally not ions. Okay, so only gases are your flavors of O2, CO2, the nonmetals, the diatomic, but gases, if any, I don't think they are. I don't think gases are ionic species. Kind of went over the sub-laws of the ideal gas law, so I will go over these a little bit fast. But Boyle's law is the only one that, so first of all, as the pressure increases, the volume decreases. So as pressure goes up, volume goes down. That's the only one that's the indirect. Charles' law, as the volume increases, the temperature increases. Generally, as the temperature increases, the volume increases, so the gases expand. And Avogadro's law, I want you to think of inflating a basketball or a bike tire. Okay? What happens in Avogadro's law? Think of inflating a bicycle tire or a basketball. What happens? You're pumping gas molecules in. What happens to the volume of the basketball or the bicycle tire? It increases. So that is another direct proportion. A little mnemonic I've generated to sort of help you learn the relationship, at least between 3 of the 4, pressure, temperature, and volume. So as an example, if you hold the pressure constant and if you increase the temperature, what happens to the volume? Okay, the volume goes up. If you decrease the temperature, okay, what happens to the volume? The volume goes down. Okay. If you increase the volume, what happens to the temperature? It's also going up. If you decrease the volume, what's happening to the temperature? It's going down. All right, that's under constant pressure. Under constant temperature, okay, this is Boyle's law. Increase the pressure, where's my volume going? Okay, it's heading down, tilting down. If I decrease the pressure, where's my volume going? Okay, my volume is going up. If I increase the volume under constant T, if I increase the volume, where's my pressure going? Going down. This is an indirect relationship. If I decrease the volume, where's my pressure going? It's going up. All right, that's Boyle's law. All right, under constant volume, increase the pressure, what happens to the temperature? Goes up. Okay, increase the temperature, what happens to the pressure? It goes up, more collisions. Okay, more frequency of collisions. Decrease the pressure. If I decrease the pressure, what happens to my temperature? It goes down. If I decrease the temperature, if I lower the temperature, less collisions, less pressure gets exerted. All right, so this is Charles' law. This is Boyle's law, and this is another variant of Charles' law. If I want to do Avogadro's law, that's the relationship between volume and number of moles of a gas. Think of inflating a bicycle tire or a basketball, and that is a direct relationship.